As a physics passion student, you have probably experienced at least once in your life a burning desire to apply physics to your daily life, right? Well, if so, consider yourself lucky today. Today is your day. So, how do you calculate the height of a building? How do you do that? Well, that's what we're going to talk about in this video.
How to calculate the height of a building using physics.
Here you have some requirements, hear me out. Number 1. Take the object that is higher in mass.
For thousands of years, people erroneously thought that heavier objects fell faster than lighter ones. It was not until Galileo studied the motion of falling objects that it became clear that, in the absence of air resistance, gravity causes all objects, regardless of their mass or shape, to fall at the same rate.
In a nutshell, according to Galileo, in vacuum, gravity doesn't care about the mass. Outside of the vacuum, the air friction does. So we have to take the object that is high in mass. The heavier the object, the less it experiences horizontal air friction. What about the vertical air friction then? Sadly, it is out of our control. Number 2. Make sure the object is in shape of a sphere. Otherwise, due to that horizontal air friction, objects that are not in shape of a sphere may change their starting position. As a result, the final position reaches the ground in less time than the starting position, which may eventually lead to some errors. Sphere in this scenario is our well-respected hero because it has 0 sides, 0 corners or edges that are going to benefit us in this experiment.
Now, let's release the object from rest at the top of a building. You don't throw it down completely. Simply release it from rest, so the object is going to fall down under the influence of gravity. As you release, press the stop button of your stopwatch and stop the time counting as you hear, not see, but hear the sound that the object fell to the ground.
In my case, I heard the sound but 1.86 seconds after I dropped the object, so time is equivalent to 1.86 seconds. And one thing that we must not forget is human reaction time. Average human reaction time for auditory stimulus is 0.17 seconds. So we subtract this number from the original one and we get 1.69 seconds. Now as I keep dragging sound again and again, write down this equation. The equation that determines the speed of sound in any temperature.
Speed of sound equals to 331.5 plus 0.6 times t. T is temperature, which is in Celsius. Yeah, the temperature matters because the speed at which sound travels through air is dependent on temperature. In my case, it is 30 degrees Celsius outside, hence V equals to 331.5 plus 0.6 multiplied by 30, and that would be equal to 349.5 meters per second.
With this information, how can we determine the height of a building? What formulas we need in order to solve this? Now we need to break up this problem into 2 parts. In the first part, the ball is falling. The time it takes to fall, let's call it T1. During the second part of the problem, the sound wave is traveling from the point of the impact to the person's ear. We'll call it T2. The total time for this whole problem is T1 plus T2, and that's gonna be equal to 1.69 seconds. So we'll save this formula for later. Whenever you get a problem like this where you have multiple variables, you are going to need to use the system of equations, and for this particular problem, we are going to need to use the quadratic equation as well. We'll come back to it later. For now, let's focus on the first part of the problem, when the ball is falling down.
The ball is falling under the influence of gravity, so we have constant acceleration. One kinematic equation that we could use is this one. H equals to V initial times t plus 1/2 gt squared. Because the ball is being released from rest, the V initial is gonna be 0. consequently, height is equal to 1/2 and the gravity is gonna be 9.81 multiplied to t squared. So we have this formula. The height of a building is gonna be half of 9.81, which is 4.905 times t squared, and this is gonna be t1 squared, since we focus on the first part of the problem.
Now it is time for us to write an equation for the second part of the problem, that is when the sound wave is traveling back to the person's ear.
The speed of sound for the most part is moving at a constant speed. It's not accelerating. Whenever you have an object moving at constant speed, you could use this equation. Distance is equal to speed multiplied by the time. The distance traveled by the sound wave during the second part is gonna be equal to the height of the building, so we can replace it with h. The speed of sound is equal to 349.5 meters per second. At the time it takes to travel back, that's gonna be t2. So here, h equals to 349.5 times t2.
Because both of these equations is equal to the height of the building, we can set them equal to each other. 4.905 t1 squared is equal to 349.5 t2. Now remember the first equations we wrote and saved for later. t1 plus t2 equals to 1.69 seconds, that is, it is going to assist us now.
From here, let's solve for t2. t2 equals to 1.69 minus t1. It now allows us to replace this t2 with that one. That's how we're gonna have 4.905 t1 squared equals 349.5 multiplied to both 1.69 minus t1. Let me do the quick math now. And 1.65171 is the answer we're going to pick. Because time is a scalar quantity, it cannot have the negative sign. And now, let's take this answer and calculate the height we have been striving to find. H equals to 4.905 times 1.65171 squared. And that's gonna be equal to 13.38156, which is approximately 13.4 meters.
What is really interesting is that 13.5 meters is an actual height of the building. So now tell me, biology, chemistry, or physics? Chemistry, they say,